I'm very, very happy, and it's a great honor, of course, to have Michael Ghil present at our monthly ClimTip webinar. So just a little bit of background. So Michael is a mathematician by training, obtained both his master's and his PhD from the Courant Institute at New York University, PhD under the supervision of Peter Lax, and has then founded, after some time, the Theoretical Climate Dynamics Group at UCLA, where he's still a distinguished research professor, but then also, I forgot for how long, is also a distinguished professor at the École Normale Supérieure in Paris. And yeah, my impression, so my understanding is, or my view is that Michael has pioneered, in particular, the application of dynamical system concepts, bifurcations, and all that already back in the 70s, has pioneered their application to different problems in, let's say, more theoretical climate dynamics with a focus on atmosphere and ocean dynamics. But his interests are also much wider. He has been working and leading projects on extreme events. He's also made very important contributions to economics and at the intersection between economics and climate, the impacts of extremes and different cycles in economics. Has also worked on population dynamics and is, for example, one of the inventors of singular spectrum analysis, which I think is across many fields way beyond climate science, a very widely used technique for time series analysis. And so, yeah, Michael has already designed with us the predecessor of ClimTip, the TTPs project, where he was very strongly involved, and is now also part of ClimTip, of course. Yes, I'm very much looking forward to the talk, which will be on non-autonomous dynamics and to help to study long-term trends and transitions in climate variability. I'm very much looking forward to that. Michael, the floor is yours.
Thank you very much, Nicholas, for this lovely introduction and for keeping it suitably short. I will now need, I think, to share the screen. Okay. Let's see. Okay, so here we go.
Yes, this looks perfect.
Okay. So about non-autonomous dynamical systems and how they help us study long-term trends and abrupt shifts in climate variability. So this is a very nice logo, by the way. Obviously, this is joint work with quite a few people, and thanks to all of them from whom I learned. And most recently, the substance of the talk involves yet another research project, which is a French-Argentinian project. So some of the people here, Nicolas Bodnariuk and Gisela Charot, and Denise Chamarella and Sabina Speicher also involved in that. And then there's a collaboration with Stefan Van Itzem and people around him. And actually, there's another one with Henk Dijkstra at Utrecht and a master student from the IMAO who spent some time with me. And I was actually planning to show some work out of that, but decided finally, given the limited time, to stick more with the one with Stefan and company in Brussels. And anybody who's interested, well, you can find stuff on this website and probably more up to date just on ResearchGate. So basically, technically speaking, this is about non-autonomous and random dynamical systems on the one hand, and even more recently about topological data analysis as applied to dynamics as opposed to static objects. So we'll talk first about intrinsic versus forced variability, short, intermediate, and long-term prediction, multiple scales of motion, and then more about time-dependent forcing, so intrinsic versus forced variability, and about pullback and random attractors, and then illustrative examples, will include the well-known Lorentz convection model, which for many people is the Lorentz model, but actually it's just one of several that he formulated and which are being still actively studied. In particular, one in 1984 model that we studied with Bernardo Mahaldi and Henk Dijkstra, but that I won't get to take case. We're going to talk about this one, but in the presence of time-dependent forcing. And then the so-called wind-driven double gyre problem, which is sort of a slightly idealized version of what happens in mid-latitudes, ocean basins. And finally, the Enso forcing of a mid-latitude coupled model, atmosphere-ocean coupled model. And then I will talk about these aspects, which are the newest in the development of this area that, as Niklas very nicely put it, I've been pursuing well for quite a while, going back to my PhD at the Courant Institute, dynamical systems and their bifurcations and so on. And so we'll see specifically how homology groups and branch manifolds come into play and what a topological tipping point is and why we care, and conclude with some remarks and references. So, to start, the object of study, so short, intermediate, and long-term prediction. This is basically a quote from John von Neumann, who, as you know, did an enormous number of things, but in particular started numerical weather prediction with Charney and Fjordhoft and some others at the Institute for Advanced Studies in the late 50s and early 60s. And who also convened a meeting shortly before his untimely death on climate. And that was published some years after his passing as a book called Dynamics of Climate. I think it's the first time that these two words were used together in 1960. Before that, climatology was essentially a descriptive discipline, part of geography. So what did John von Neumann say in his introduction to that meeting? Well, the initial value problem, so dynamical systems and predictability, the initial value problem, which is essentially numerical weather prediction, is the easiest one. And indeed, weather forecasts for a few days are pretty routine, and often they're even correct. Then there's the asymptotic problem, long-term climate. That's a little harder, but it's really the intermediate problem of what's sometimes called low-frequency variability, which involves multiple equilibria, long periodic oscillations, intermittency, slow transients, and what's now called tipping points is the hardest. So basically, this is a sort of problem that we want to talk about. Well, global warming and its socioeconomic impacts, the problem has become one of great interest and still fairly unpleasant debate between miscreants who don't believe the scientific results and the ones who do believe it, but in any case, a great amount of scientific uncertainty. So this is actually from an earlier so-called assessment report of the Intergovernmental Panel on Climate Change, 2007. I think that most of you know about the IPCC. Basically, any scientific problem people work on, if there are already 2 or 3 people working on it, it's worth at least one acronym, and here there are hundreds of people involved, so there are second and third order acronyms. So this is the assessment report, and this is working group 1 that deals with the physical problems, and this is a summary for policymakers. So basically, I still like this one because it's, in some sense, the most explicit one. So basically, you see some simulation of the past century. Okay, so this is just the global average temperature, simulation of the past, and then prediction of the future. So this was published in 2007. It was very close to this. And at the time, these different colors were simply called scenarios that the other working groups 2 and 3 came up with. And you see that for each one of these, there is an uncertainty bar, which is basically not a scientific statistical estimate. It's just a spread of the particular models involved in that cycle of the IPCC work. So basically, you see that there are still a few degrees which are uncertain. Furthermore, actually, this thing which looks like it's a pretty high certainty, actually, the mean is off by some degrees, but let's not get into that. There's a more recent version that I have borrowed from Nicholas, who kindly made his slides from a month ago available. So this is for the sixth assessment report. And now, instead of having scenarios, we have SSPs, which are shared socioeconomic pathways, which replace the RCPs, which were between the first report and this one. Okay, representative concentration pathway. But you see that there's still quite a bit of uncertainty. And while there are many aspects of that uncertainty, I really want to talk about the uncertainty involved in the due to the intrinsic variability. So, it all started with a report to the National Research Council, which is a working arm of the US Academies of Science, Engineering, and of Medicine. So a report that was headed by Jules Charney, probably the most prominent meteorologist of the generation. The question was, if I double CO2, what happens to the temperature? Global temperature, this stands for averaging. So basically, the thinking at the time was in terms of the scalar linear equation. So if that is the case, what will happen is this, the red line. But we know very well that the climate is not in equilibrium, actually. So what about non-equilibrium sensitivity? So let's say what would happen if it were purely periodic. Let's say that the El Niño Southern Oscillation would really be purely periodic. Well, the mean would still go up. There's no way of, quibbling with that, although people still try to do so. But then the amplitude and the period of the oscillation could change. And then here I say, what about some real stuff? In other words, both chaotic and random. This is out of an article in the Encyclopedia of Global Environmental Change. What would happen is still the average will go up, but a lot of other things will happen. And that's sort of the question, what other things are happening? Okay, so now I apologize to those who are less mathematically inclined, but I hope that there are some who are mathematically inclined. Okay, so we're looking at the standard dynamical system theory is basically for constant coefficients and constant forcing. But here, that's not the case. So there's time-dependent forcing and coefficients that arise from the parametrization of the models that have to do with clouds and cloud radiation interaction and so on, change in time. So we have to look at this open system that gets energy from the sun and sends it back to interplanetary space. So fluxes of mass, momentum, and energy between the system and its surroundings are present. So there is this framework of non-autonomous dynamical systems, which is more appropriate for what we're dealing with, in which the fluxes depend explicitly on time. So probably the first contribution of this kind goes back to George Sell. I'll have references later. So we have two coupled systems. So X and Q are vectors. So the time derivative of X depends on both X and Q, but the time derivative of Q depends only on Q and not on X. That's why George called them skew product flows. Okay, Q is a driving force for X. And then come pullback attractors that essentially were started by a paper by Hans Crauel and Franco Flandoli, who were postdocs of Ludwig Arnold, and defined pullback attractors. And then there's something that was called snapshot attractors by Ed Ott and associates in the physical literature, and where the notation for the case of the forcing being random has been changed here. So now it's a differential of cap x. The signal or the, well, think about it as a climate signal is a function of x and q. And what happens in addition is, okay, I have a driving that is a Wiener process. And so that's why I need these Ds, because the time increment of t is proportional to the square of the time increment of the Brownian motion. So more generally, studying explicit time-dependent forcing or coefficients requires these non-autonomous dynamical systems. Nomenclature is a little bit confusing because it applies to both deterministic and the random case. And the commonality between the two cases is the independence of the driving force, whether it's Qt or Wt, and the so-called semigroup property, which, as I'll show you, just means that if I go from T to T1 and then to T2, it's the same as going from T to T2 directly. So likewise, pullback attractor is used both for the deterministic and random case, but for the specific random case, one also uses random attractor. So why do we need this? Well, consider this very, very simple example of a scalar linear ordinary differential equation. So x dot is equal to minus alpha x plus sigma t. This is a dissipativity, which is very important, although there are some people like Thomas Stehl who also deal with a Hamiltonian case, but we're only going to deal with a dissipative case. So alpha and sigma are positive. When there's no forcing, it's obvious that the stuff just decays from whatever initial state to zero. And also all solutions converge to this fixed point as time proceeds to infinity forward. Now, what when we do have forcing? So now, at each time t equal t1, say, we have to pull back. So when I'm there in person, I can do this on the podium, but here I can't do it on the podium. So we just have to pull back like that and start at some time s equal to s1, which is much smaller than t1, and see where the flows takes us at t1. So let's say that the observing time here is t1. In this case, there's no forward limit because the forcing is unbounded. And so we know that it's just going off, but there's no specific forward limit. But there is a way of defining a backward limit. So if I pull back to S1, I will see that all these trajectories converge at T1 closer and closer to this straight line, and even more at T2, or when I pull back to here. So there is a straight line, which is the pullback attractor. So I will try to also show this by an animation. Okay, so we have here a little animation. So again, I'm trying to see what happens when I observe here, okay? So I pull back, you say pull back, and as I pull back, it converges better and better to this straight line, okay? So that's what happens in the very simplest case. Okay, sorry. Okay. So in the random case, there is also a counterpart of this, and we're going to look at that more closely in a moment. So it's this is a counterpart for randomly forced dynamical systems of the so-called geometric theory of ordinary differential equations. It allows one to treat stochastic differential equations and more general systems driven by noise as so-called flows in not just in phase space like for ODEs, but in phase space times probability space. I'm skipping what's below because it's more technical. So essentially there are these equivalences. Well, this is a little bit tongue-in-cheek because Ludwig Arnold in Bremen, well, V.I. Arnold in Moscow was essentially a father of the geometric theory of ODEs, but there's no family connection between the two. So the more complicated case of what I was showing you before is this sort of random attractor, where again I have to pull back to get at any snapshot. So what I observe at a given time is no longer just a fixed point as it was in the scalar case, but it might be something more complicated. In any case, I have to pull back further and further to converge better and better to that particular snapshot. So again, just one more snapshot of quasi-theoretical stuff for those who are interested, and then we're going on to the applications. Okay, so these are things that I already said, but now what I have to say is that there was a little bit of confusion in the climate literature because there's this group coming from physics where we're using the concept of snapshot attractors, and it looked for a while that it might be something just less sharply defined than the pullback attractors, but it's actually not. It is just a forward attractor in the case of time-dependent forcing. So what happens is that these snapshot attractors, in other words, forward attractors in the case of time-dependent forcing, exist only for bounded forcing and might be non-unique when they do exist. When they do exist and are unique, they are so-called uniform attractors, which actually were formulated by Alain Aron before these, well, not before George Sell, but before this stuff. So here there are some references, and again, I don't know whether you want to put on the website. I think it would be good to put also the slides, not just the video. Okay, so here I just have an example like the linear scalar thing here. Okay, I have one for periodic forcing. So basically, attractors forward, pullback, and uniform. This is the forward attractor. I start from the same time, and all trajectories will basically, no particular trajectory will okay, let me say this differently. They they do converge to this attractor, which is a red line, which is a counterpart of this straight line. Okay. So, but the time-dependent forcing has to be bounded for a forward attractor to exist, which is not the case as far as we know, unless we do something with anthropogenic greenhouse gas forcing. Okay, that would just keep going unless we do something. And well, while we're doing something, it might not quite be enough. So it has to be bounded for a forward attractor to exist, but the uniqueness is not ensured. Periodic forcing ensures both existence and uniqueness is to in turn ensure that the forward and pullback attractor are the same, and they both correspond to a single uniform attractor. Okay, so this picture is actually taken from the book by Caraballo on hand. So what my remark at the bottom, nota bene, snapshot attractors of physical literature are not like PBAs. They are like forward attractors in this context. Okay, so examples. Impact of climate change on intrinsic variability. So essentially the kind of thing that has been dealt with so far, this you will recognize is essentially just the Lorentz 1963 convection model, to which is added an oscillator, okay, that's coupled to it, okay. In this case, it is two-way coupling, but in fact, what was done was just essentially to set V equal to 0 and W equal to 4, okay? And so there's various pieces of work on this. So if this is a probability density function in the XY plane of the model, essentially what it does, it shifts the weight from being equal on both feet to being more heavy on one side rather than the other. Okay, so it's something, but it's not much. It says the variability, essentially the nature of the variability stays the same. it still does these things, but it's more on this side. So now I'm going to give you these examples, which are sort of intermediate. They're no longer just a scalar equation, okay? Example of bifurcations and, well, the hierarchical modeling, I don't have the time to show you, but the simple things which we've seen, will see here in the next couple of slides, have been verified with much more elaborate models. Okay, so this is a particular model of this kind, still highly idealized, of the quasi-geostrophic equivalent barotropic potential vorticity equation. So therefore, quadratically nonlinear ODEs, okay? This is just the time derivatives. These are the linear terms which have to do with the Coriolis force. And here are the nonlinear advection forms, and these are just prescribed time-dependent functions. So the bilinear terms are like that. You're familiar with this sort of thing. So it is essentially due to some work of Stefano Pierini before the collaboration. So the time quadratic terms are conservative and the linear terms are weakly dissipative, while the system is unstable for reasonable parameter values. For autonomous systems, we know that these properties can lead to chaotic solutions that live on a strange attractor. Here they lead to the existence of a pullback attractor. So I won't go into the details. You can find them in this paper. But basically, this is a time-dependent forcing. This is sort of a time-dependent forcing of a roughly decadal nature, something that would be, for instance, imposed by the Pacific decadal oscillation, or sometimes called Pacific decadal variability. And these are the solutions. So there are really four variables. So it's hard to show that in the plane. But what is shown here is a projection of just two of the variables. I think it's it's psi1 and psi3. So you start with points on this initial square, and you have trajectories which in one case are on the side of the autonomous systems bifurcation, for which the autonomous system is really just relaxation oscillations, periodic but not harmonic oscillations. And on the other side over here are in the case in which the autonomous attractor is chaotic. So you see that again, there is rich behavior, which is both due to the intrinsic variability and to the forcing. And in this case, we were able to show, again, I won't go into the details exactly how this is generated, but basically the warm colors correspond to chaotic behavior and the blue colors correspond to stable periodic behavior. The square is the same square as you want over here. So it just shows for which initial conditions we get orbits which correspond to periodic or to chaotic behavior. And again, the important thing is that there is a coexistence of two kinds of behavior, the regular and the irregular one. And although there wasn't enough time and computing power to work this out in great detail, but it's pretty clear that the basin boundaries are fractal. Okay, so now I'm coming to the coupled model. Extratropical low-frequency variability with Enso forcing. Again, I reduced with a coupled model study. And these slides are essentially from Stefan. Analyze a pullback attractor and their properties for this model. So the tropical model is essentially a recharge-discharge oscillator from Fei-Fei Jin, according also to his work to Axel Timmermann, who was his postdoc for a while at Hawaii. And this is the extratropical model, which is this coupled model that we had worked already with Stefan and with group previously. So basically, this is a total of about 36 ordinary differential equations, 16 plus 20. So it's not quite a toy model, it's sort of intermediate. So in the case in which the tropical oscillator is periodic, you use parameter values for which it is periodic. What is plotted here is the leading Lyapunov exponent, as you know, a measure of predictability, as a function of the coupling and of another coefficient. I won't go into that, but really what I would like you to see, okay, so the coupling coefficient in one case just gives you one single attractor. In this case, there seems to be a very strong evidence for the coexistence of two distinct, if you wish, local PBAs. I mean, there is some communication between them in the chaotic case. So just a footnote, these Lyapunov exponents, which are well known in the autonomous case, were shown by Ghil in a paper in 1984 to also be well defined in the time-dependent forcing case. So this is now again for the chaotic forcing. So you see that there's coexistence and communication between the two. So each variety of pullback attracts at mid-latitudes, multiple ones can coexist for certain ranges of forcing parameters. Two stable pullback attractors can be present. In the chaotic forcing case, transitions between those two bases of attraction may occur, tunneling through the boundary, but on very long time scales. I'll skip the resonance, don't know time for that. In the periodic forcing case, the two coexisting PBAs are quite robust to small initial perturbations, not true for the chaotic case, as I said before. So now I'm coming back to this Lorentz random attractor. So again, this is a stochastically perturbed Lorentz 1963A model with the usual parameter values, Rayleigh, Prandtl, and wavelength parameter, the usual ones for the deterministically chaotic strange attractor, of which you can find many images on the web. So this would be, this is essentially the standard one, to which we add multiplicative noise, multiplicative because you have the X, Y, and Z in front of the random noise, okay? So this is from this paper from 2011. So I think in spite of the fact that this literature is now a couple of decades, well, 3 or 4 decades old, when we started this work in the first decade of this century, there was no image of a pullback attractor with any sort of revolution. There was one example by Schmalfuss that had where you could see the individual points, but no such thing as an approximation of an invariant measure of a PDF like we have here. So we compute the probability measure of this random attractor at some fixed time t. Remember that observation time, and for fixed realization omega. So this is not the usual forward flow of the Fokker-Planck equation that you're familiar with. We show a projection of the three-dimensional thing onto the XZ plane with a multiplicative noise. So this is the index for X, Y, and Z. And there are 10 million of initial points. Okay, and this essentially is the density of the invariant measure. So these ferocious eyes are the convective fixed points of the usual strange attractor. But then what you see when this starts moving, then it becomes much richer. So again, I will refer now to a rather spectacular video that many of you have already seen and that people have tried to steal from us for other purposes, but not quite so yet. Okay, so what you see here essentially, this is just 1 minute, don't be afraid, is something that you wouldn't have suspected. So clearly there's flow that is in which the invariant or sample measure is carried by the deterministic attractor, but then there are certain things like this concentration near the origin and this artesian fountain which you could have never suspected just from the deterministic thing with time-independent forcing. Okay, so there was much to look at, and so we started looking at it with the tools of algebraic topology, because clearly this was, there was very rich behavior and you had to understand it better. So it turns out that, like deterministic chaos theory, this algebraic topology goes back to the work of Henri Poincaré. I must say that there are actually many meteorologists who think that actually Ed Lorenz discovered what's called now deterministic chaos, but that ain't quite so. It was really Henri Poincaré who discovered this in his work on celestial mechanics, and he drew the analogy between the weather of the planetary system and the actual weather on Earth. He talks explicitly about the fact that weather was similarly affected by sensitive dependence on initial conditions in this book, Science et Méthode from 1912. So he also built on a few earlier results of Riemann, Betti, Jordan to create the field of algebraic topology, which he called analysis situs. And this work combines these two strands from Henri Poincaré's heritage. So it's due to Denise Chamarella and her group at Buenos Aires, part of which is fortunately now at the École Normale in Paris. So we're proceeding on this with due diligence. How to unveil the topological structure of a flow in phase space. So by computing topological invariance using homologies, so you start with an n-dimensional point cloud and you land with a homology. So you approximate points as lying on a branched manifold. A branched manifold is simply an approximation of, in this case, of the complicated structure of the strange attractor, which has many parallel sheets. So if you drill through it, you get something like a Cantor set. Find a topological representation for the branch manifold, obtain an algebraic description of the topological structure. Okay, so this is what the branch manifold looks like. Okay, and the homology groups correspond, the first one just to the whole thing being connected or not. So it's connected, it's a single connected object. And the number of holes, so there are two holes, and then there are no higher dimensional holes, although the dimension of the attractor, the fractal dimension is 2.06 or something like that. So you try to locally approximate this by d-disk using singular value decomposition. So you can handle shorter noisy time series, which you cannot with other approaches to this sort of topology via knot theory, which only carries you through dimension 3. Build a cell complex keeping track of gluing prescription. So it's called branch precisely because you have to take the two manifolds and glue them along a line where you exchange from one wing of the butterfly to the other. Compute homologies and orientability properties of the cell complex so as to identify the structure. So this just described what I described to you before. And here you have essentially the result of this analysis, which again, it's published in this paper. And I'm just going to show it to you here. So for different parameter value, for different time snapshots, observing times, which are very close to each other. So these are non-dimensional time units in the convection problem, 40.09, 40.18, 40.27, and we've since verified this in another paper even more closely, so the transitions are clearly sharp. Here you have, so these are just the approximations of the point cloud, and these are actually the branched, the branch manifold approximations. Here you have the number of holes is equal to 3, here it's 10, and here it's again 4. So these transitions are sharp, and so they enrich the classification of so-called tipping points beyond the classical bifurcations of autonomous dynamical systems. So this classification is due to Pete Ashwin in a paper in the Phil Trans. B-tipping or bifurcation-due tipping, this is what we knew before, which actually we knew back to Euler, who solved the first such bifurcation problem for the buckling of a beam. As the force increases, low change in the parameter leads to a system passage for classical bifurcation. N-tipping, random fluctuations lead to the system crossing an attractor basin boundary. And then the most interesting one so far, as distinct from what we previously knew. So, this is 2012. Basically, we knew these things for a few decades, but this is sort of fairly new. Rapid changes lead to the system losing track of a slow change in its attractors. So all three types involve an open system. So, that's why, as I said, starting with the study of the closed system helps us understand what happens for the open one. So concluding remarks, first for random dynamic systems and random attractors, change of paradigm from closed autonomous systems to open non-autonomous ones. Random attractors are spectacular. They are useful in ways that I would still need time to explain and just starting to be explored for climate applications. Work in progress, study the effect of specific stochastic parameterizations of clouds and other things on model robustness. Application to model and intermediate models and GCMs or ESMs, applications for climate sensitivity and for predictability. And in terms of the topological side of this toolbox, a change paradigm from static topological data analysis, which has also already an acronym TDA, to dynamic, chaotic, and non-autonomous systems. TTPs are sudden changes of homology group from one snapshot to the next. And furthermore, what this other project that I was mentioning to you in which we're involved does, it looks at, in addition to what I talked about so far, to a directed graph of flow direction in phase space. And again, the work in progress is studied as counterpart of specific TTPs in physical space, counterpart of specific TTPs for distinct clipping and climate tipping elements, again, applications to intermediate model GCMs, etc. Okay, so, why algebraic topology and why TTPs? It's not yet taught in school, but it should be. The Nobel Prize in Physics in 2016, shared by 3, was open doors to study new states of matter. Topological concepts in physics were decisive for their discoveries. And Abel Prize, which is sort of the counterpart of the Nobel Prize in Mathematics, 2022 was the single recipient was Dennis Sullivan for contributions to topology and in particular its algebraic, geometric, and dynamical aspects. So topological data analysis only being applied widely for static problems, but not yet dynamical ones. Very few, but I can answer questions if there are any. TTPs can help us extend successive bifurcation trees beyond classical bifurcations and even beyond newfangled TPs that have arisen in the NDS concept. TDA in phase space can be complemented by the TDA of new regimes of behavior in physical space. And such coupled TDA could help bridge the gap between understanding nonlinearities at large scales and fully developed multi-scale turbulence. Okay, and then I have some references, but I won't take them through you in detail. Thank you very much.
Thank you very much, Michael. And the floor is open for questions. And to give people some time to think about their questions, maybe I start with the first one, which isn't on any of sort of the specific content, but more on maybe some so let's put it this way. So I think you have contributed and you have been involved in establishing several, let's say, larger frameworks or so in like mathematical concepts, let's put it that way, in the climate sciences. And I guess this has started at some point with sort of convincing people that things can be nonlinear.
Well,
And
that is still difficult, as you know, Nicholas, from the previous project, in which a leading person that was participating, and there's a little bit not quite to the IPCC class models, but sort of pretty detailed models, was asking how come this model is not nonlinear, because there are thresholds for parametrizations and so on. So it ain't the same thing. Sorry for interrupting. Please
no,
go
but
ahead.
that's exactly in the direction I'm about to ask. So,
Okay.
sort of from trying to convince people that not everything is linear to sort of establishing concepts like bifurcations, to going further towards non-autonomous dynamics and now algebraic topology. So you have been successful in establishing quite a few concepts over the years, but there is a sort of a concern that I would have is that the concepts are getting more and more complicated, and you can't expect everyone to study math. So how is this done? What's like how do we?
Well, we all study quadratic equations at some point, right? I mean, quadratic algebraic equations. The difficulty is extending the really mastering the analogy between that very simple thing, which leads to parabolas rather than straight lines, to a saddle node bifurcation whose normal form is just a parabola, and how come that these sticks that have millions of variables behave according to such laws, which are still relatively simple. Okay, counting holes is not really difficult. Okay, and to the extent that machines are learning more and more and can even teach us more and more, it might be possible. I mean, I've led a life at the gluing point between between the mathematics and the physics, and I'm trying to translate. Although, like that movie, the famous movie says, some things get lost in translation. So I'm doing my best, and we had this previous conversation with Quat in testing the system, and he told me, well, what stochastic stuff got to do with climate? Well, there is a guy who got a Nobel Prize for that, or part of a Nobel Prize.
Yeah.
So what have clouds to do with Brownian motion? Well, it's a matter of developing that feel for the analogies between simpler things and much more complicated as distinct from complex. Complexity in physics has a somewhat well-defined meaning, while complicated just means I don't understand it. So, we have to try to go from I don't understand it to well-understood complexity.
Yeah, fair. All right, there's one question in the chat that I'm going to read. So, dear Dr. Ghil, in the context of non-autonomous dynamical systems, how do you see the interaction between short-term climate variability and long-term climate shifts influencing our ability to predict critical climate tipping points, particularly with respect to abrupt events such as polar ice sheet disintegration or shifts in ocean circulation?
Well, the whole point of the need for non-autonomous dynamics comes from this multi-scale character of climatic variability. Because if you can just, why was autonomous, there was no need for the word autonomous, because simply dynamical systems, dynamical system theory only dealt with autonomous systems, okay? So, it's a little bit like Stanislaw Ulam said that talking about nonlinear physics is like talking about non-elephant zoology. Most of zoology is not elephants, okay? Most of the physics that we're dealing with of environment and so on is non-autonomous. But in any case, you used to talk about so-called what was called in physics adiabatic or quasi-adiabatic change. In other words, change that is slow with respect to the intrinsic timescale of the system. So the simplest situation is that of an oscillator, okay? Let's say that you have a nonlinear relaxation oscillator for constant parameter values, and then you try to change the parameter very slowly. So it's so slowly, in principle, adiabatic is infinitely slowly, it's so slowly that it can quietly change its behavior as long as it's continuous and then jump when you reach the bifurcation point, okay? But that's not the situation. So what you do when the time scale of the forcing is similar to that or not very far from what's called in nonlinear engineering mechanics, the detuning between the forcing and the system behavior, is that you use these concepts of non-autonomous dynamical systems. And I can't help it. I mean, I'm trying to explain it as simply as possible. But again, Einstein said, make everything as simple as possible, but not any simpler. Okay? So sorry, guys and gals, just gotta learn some of this stuff. Now, I can start to do a little bit of advertising before the product is quite on the market, but I'm trying with two French associates to complete a book, and I hope it will be done this calendar year, that is mathematics for the environment, and it ends with a chapter on non-autonomous dynamics. Okay, so I hope that will be helpful, but you've got to make an effort. It doesn't really come cheap.
All right. Any further questions? Maybe let me ask a sort of follow-up question to the last one. How do I say this? So, in the application of the, I mean, we have discussed this to some extent, the application of the concept of non-autonomous dynamics to paleoclimate. And there, of course, it's very obvious why it makes sense, because you have the external forcing. And my understanding is that it is still not quite clear. So there's sort of two classes, sort of two theories on paleoclimate dynamics on these long time scales, which is on the one hand, so concepts that are based on synchronization ideas, that there is some sort of synchronization or phase locking and so on. And the other one would be all the sort of resonance class of theories. Do you think?
Random?
Pardon me?
What was the second one?
Resonance. I mean, the sort of
resonance.
stochastic resonance, and then everything that developed on top of that in the decades.
Look,
my question is there? Do you see a chance that we can, using the data and the models that we have, but sort of from the perspective of non-autonomous dynamical systems, do you think that there is sort of from a theory side, there is something to do that will clarify this question?
Well, Nicholas, we wrote a couple of papers on that together with some very nice associates. The problem is that we don't have enough data.
Yeah.
Quite frankly, it's really embarrassing. And my colleague, I've known Isaac Held since we're both doing PhD theses on either side of the Hudson River, he at Princeton and I at NYU. And we used to meet at the climate committee of the National Research Council. And, he also wrote a paper on hierarchy of models and so on. But I remember that in conversations we had, he used to express dismay at the fact that the biologists have been so much more successful in applying novel and deep concepts than climate scientists. And, that's expressed that I was really recently reminded by Aviatar Bach of the fact that, he expresses some of that in that paper. And, look, in the so my thesis was published in the mid-70s, and the PhD thesis of one of my excellent PhD student, Bernard Legras, was published in 85. Well, we worked with, I worked essentially on this multiple climate problem, and he worked on blocking, and neither one is resolved 80 or 70 years later. It's really dismaying, the little progress. I mean, bigger and bigger models and no real, there are more theories. I mean, in that paper with Ken Richards, we reviewed in that table, I don't know how many tens of models of the mid-Pleistocene transition. There are simply no data, but even for problems like blocking, for which there are data, there's no willingness to agree. There is a knee-jerk reaction against mathematics. I won't repeat the story that I told you and other younger associates that I particularly liked, about talking about something that happens in big models when you couple them, and they ran away, and he thought that could be easily fixed. And I sort of tried to show him on a blackboard again at the climate committee of the National Research Council that it wasn't so for a simple scalar equation. And the answer was, Michael, well, that's just mathematics. Okay? So, if people refuse to believe, I mean, Galileo said it, that mathematics is the language of the universe, and if you're a believer, maybe of God, there is nothing else that can really describe precisely and convincingly what we observe. But if you haven't learned it in kindergarten, and of course kindergarten is for scientists graduate school, well, for some people it might be too late, and they might not be willing to assimilate it no matter what. But other than make it as easy as possible, but not any easier, I don't know what to do.
Yeah. All right. Thanks for this. And also in general, thanks for giving this wonderful talk. So I'll hand over to Kurt again to do the announcement for next time, I guess.
And thank you for everyone for joining. Our next webinar will be in the first Tuesday of November, but we haven't clarified our speaker yet, so we will update you once we know. Thanks everyone for your time. And Michael, thank you again.
Well, thank you for inviting me and for sitting through it. Okay.
Thank you very much, Michael. Take care. All the best.
All the best.